My name is Chris Lapp. I'm a technical solutions architect at Cisco Systems. I lead the technical side of the media and entertainment vertical. And today I'm going to be talking about a new version of PIM. It's called PIM flood mechanism, and very specifically, we're going to focus on what's called source discovery with PIM flood mechanism. But in order to get to the new stuff, we kind of have to review what the old stuff is. So we're going to go over a background of PIM dense mode and PIM sparse mode. And we're going to talk about PIM flooding mechanism. We're going to talk about the source discovery portion, a little bit of practical use cases and deployment examples, and then talk about where this is in the IETF. So PIM dense mode is the oldest multicast routing protocol that is commonly used today. In fact, some people actually don't even support it anymore because sparse mode kind of replaced it in a lot of cases, but there are still a few use cases that use dense mode. It's a flood and prune mechanism. That means that anytime you have a multicast, it will flood it out to the entire network and then prune where it doesn't actually need it. So there's no single point of failure in dense mode. It's good in that sense where because it's flooding out to the whole network, it ends up taking the best path eventually. It works reasonably well when you have a moderate number of low bandwidth streams, but as soon as you have a large network with a lot of dense multicast, it's going to break down really quickly. Again, other than some very specific use cases, it's not really used today. So what that visually looks like is when you have a network, the first thing that happens is all of those multicasts, or that multicast stream, if you have one specifically, will flood to all routers inside of the network. Anything that's running PIM will get this packet, the actual data packet itself. Once it decides where it needs to go, so in this case I have one receiver, it will then send a prune message when it needs to remove this flow. So it'll prune it slowly from the network everywhere it doesn't actually need to be flooding that. Eventually, building what is the optimal tree at the end of that. So that means with something like SMPTE 2110, if you were to do PIM dense mode, you're going to oversubscribe your network because it's just flooding that traffic pretty well absolutely everywhere for at least a large portion of the time. So because we started to use multicast more, PIM sparse mode was invented. There's two models of sparse mode, one for ASM and one for SSM. So we'll talk about ASM first. It is quite complex. Eventually, though, optimal forwarding happens, and we do end up getting stable packets at the end of it. This needs to use something called a rendezvous point, and that rendezvous point is built using something called star Gs, even when no source is present. That means if I have a receiver that joins a multicast group, I'm actually going to build state in the network towards that rendezvous point, even if that source doesn't actually exist on my network. Because that star G means anything that is at any address sending this group, I want to join it. So you basically build that tree towards your receiver automatically. When you eventually get the source, there's something called a switchover that introduces a traffic disruption from a source tree to the shortest path tree. So if you're doing media flows, there could be a point as you're joining that group that it suddenly just blips and then starts working again. That's that switchover between the trees. This is a configurable item in a lot of cases where you can stop that from happening though. The other problem with sparse mode ASM is that when that rendezvous point goes down, another rendezvous point has to be elected. If it's a dynamic thing, it's still a single point of failure because it requires additional configuration and election processes and things like that. So there's a portion of time where you are in a failure state before that new rendezvous point comes online. So just to go over how PIM sparse mode works, I have a little network here. I have one router designated as my rendezvous point. I have a source and I have a receiver. So this was the original version of sparse mode, specifically targeting any source multicast. You could essentially equate any source multicast to IGMP v2. So the key function of source discovery here is done using the rendezvous point. So what happens here is that I have a star G join for my receiver. So this receiver is going to build state and ask that rendezvous point for the source. So then what's going to happen is that is going to build what's called a shared tree. So anything from the rendezvous point towards that receiver at that multicast group is going to travel down this shared tree in the initial state. Maybe I'm going to then start sending traffic from my device. So that traffic is going to be received by what we call the first hop router. And the first hop router is going to send a unicast source group register towards that rendezvous point. Once that register is sent, the rendezvous point actually creates a SG join towards the source so that that receiver can then start sending traffic towards the rendezvous point using something called the source tree. That source tree now has traffic going towards the rendezvous point, so that source is set up. I send a unicast register stop towards the rendezvous point. At this point in time, now I have traffic flowing. But I told you there's a possibility that you have an interruption here. What's going to happen is technically I could switch my traffic from that first hop router to the last hop router using a different path. This is going to cause an interruption. You can configure this to do it or to not. But as I said in the beginning, this is extraordinarily complex. This requires a lot of configuration in your PIM domain for multicast to have all of this working properly. So just using the same topology that we used before for the dense mode to show you what that looks like. So initially, the traffic will use the shared tree, which is started at the rendezvous point. So I'm going to send that traffic down. It's going to make its way all the way to the receiver. And then once that entire process of sparse mode is set up, I'm probably going to switch to using the shortest path tree from the first hop router to the last hop router. Again, that's the shortest path versus the initially set up tree. We made things a little better. We invented a submodule essentially to sparse mode for source-specific multicast, or you could equate that to IGMP v3. The problem with this is that you cannot simultaneously do source-specific multicast and any source multicast with the same multicast group. It can either be one or the other. It can either use the RP or it cannot. So if you have just one device in your entire network that does not support SSM and does star G joins, you are unable to use SSM. So it's completely gone off the configuration there. So because it is simplistic, if you can do it, it makes a lot more sense. It allows you at the beginning, instead of doing star G joins, to explicitly do SG joins. So you save that that changeover from the shortest path, or from the source tree to the shortest path tree. It does simplify configuration quite a bit, but as I just said, it does not support star, G joins. So that being said, we've been using sparse mode for a long time, and it's about time we kick it to the bed. It is good in very specific use cases, like especially a spine leaf network. It makes a lot of sense. It's the same hop. Your shortest path tree and your source tree are probably going to be the same. It's relatively easy to configure in those instances in a very static spine leaf network. But as soon as you have these large service provider networks that could have many, many routers in the middle, it doesn't make a lot of sense because you're going to have to elect somebody to be the RP. That traffic's going to have to get flooded towards that RP and then possibly dispersed from the network. So in comes PIM flooding mechanism. So PIM flooding mechanism generically is a mechanism for sending any information throughout a PIM domain. So we use TLV messages to send this information. It's not actually multicast state, so it doesn't build state in the router. It just sends messages and allows us to build a database about where things are. It includes originating router addresses. It includes the RPF, or the reverse path forward check addresses, so that you can actually check and make sure that your multicast is accepted on your router. So the way it works is essentially that first hop router, when it receives a message that we want to flood out, it's going to send it to all routers in the domain. Just a little TLV management message, essentially. No different than a regular control plane message on a network today. So that's going to get flooded out everywhere that it needs to be. Now, in terms of source discovery, so source discovery messages are a specific TLV message that we use as part of PIM flood mechanism. So what happens is when this source sends traffic, the initial data packet is actually detected and dropped by that first hop router. So we don't get that first data packet when it first starts sending flows. The first hop router is going to send a triggered PIM flood mechanism source discovery message out that contains the SG information, but no actual multicast payload data towards the entire network. So everyone who's part of that PFMSD domain is going to receive this message so that it knows where that S and where that G are without having to do any rendezvous point or anything like that. And it is forwarded hop by hop. So now, once that is sent out, all of my routers know about the SG state. So essentially, we get that one benefit of dense mode where the entire router knew about the source state without being dense in terms of sending a lot of traffic. So once the PFM messages is sent out, maybe I'll do my join, and then there we go. So all routers now have my SG state, right? Cached is the source. The source will keep sending, but the first hop router initially drops packets if no one's joining the stream. So if I don't have an IGMP join or a PIM join coming into that first hop router, it's just going to drop the packets so it doesn't flood out anywhere it doesn't need to go in the network. Once the receiver sends an IGMP report for the G or the SG, we will then start to send out that payload data. So the last hop router, which is the one connected to the device receiving the flow, has that SG state cached because of PFM-SD. It can automatically join the shortest path tree without having to do anything else because it knows exactly how to get there. As you can see, I'll do that IGMP PIM join, so the receiver's asking for the flow, and because I have SG state, I can automatically build that shortest path tree down towards the receiver. So why is this important? It's extraordinarily easy to use. It's very simplistic configuration, and essentially, multicast is now plug and play on a PFM-SD network. All routers know about all active sources. We don't have to worry about rendezvous points, no unnecessary data forwarding towards that rendezvous point. You only join the tree when a source is available. If that source is not available, you actually don't conserve bandwidth by joining the tree. Removal of all RP configs. We don't need that anymore. No exchange of data registers between RPs. No switch over from that source tree to the shortest path tree, and hence no traffic disruption. All forwarding is always done along shortest path trees, and it doesn't have a single point of failure. There's, every router knows about the entire SG state of the network, and so every single router can get to every single source based on how it understood that PFM-SD message as to where to get to that S. But the most important part is it supports star G and S, G joins. So if you have a device that only does IGPv2, you can still use this. And what will happen is you'll do a star G join, and it'll actually build individual SG state for every single multicast at that group. So what happens if a router goes down? If there exists multiple paths, we're just going to join another path. Everyone knows about the entire tree, so we just join the next one, the next best. If parts of the network no longer have reachability to the source, PFM-SD state is retained for up to 3 minutes, and it recovers as soon as reachability is restored. So as soon as that path comes back up, we automatically reestablish the ability to join. When a link and router comes up and PIM neighborship is established, the neighbors automatically send updates with their cache discovery state. So you don't have to worry about sending anything. It's just an automatic process to detect that next hop inside of the PFM-SD domain. Source deliveries are sent periodically every 60 seconds. So once you have that SG state cache, we send updates to that roughly every 60 seconds in its current initiation. So what does that look like as a practical deployment? I said, spine leaf networks, it still makes a lot of sense to use the rendezvous point methodology because it's just this, one single little hop up from leaf switch to spine back down to another leaf switch. But what about a large service provider network where you have maybe a spine leaf in one location, you have a venue in another location, maybe you're remoting in and connecting to an OB truck to get some camera feeds or something like that. And inside is just a regular service provider or maybe your own dark fiber kind of multicast network. You can use PFM-SD here. Maybe the entities on the outside don't necessarily support PFM-SD, so in that case we can use a combo where just the network in the middle is doing PFM-SD, and we do essentially MSDP shared sessions between all those entities on the outside if they don't support PFM-SD. But this allows us to have multiple sources for any source multicast. It actually makes bandwidth management and bandwidth utilization extraordinarily efficient. The convergence of multicast is faster, and there's no shared tree or no rendezvous point. So feature status, what is this all about? This is not just something that was kind of thought up. This is actually an IETF piece of work. The PIM working group adopted it, and it's actually RFC 8364. So if you want to watch that RFC, you can go look it up. It's currently actually adopted and already in production across multiple media entities in Europe using our switches. And honestly, it's extraordinarily robust and working well, and we haven't seen any failures with it across the multicast domain. The only question right now is how far does it scale, which is what we're kind of testing out right now.